In 1935, Albert Einstein did something deceptively simple. He wrote down a thought experiment, not a machine, not an equation heavy paper meant to impress specialists, but a clean, logical argument. And that argument quietly suggested something outrageous. It suggested that quantum mechanics, the new theory everyone was celebrating, broke one of the most sacred rules in physics. That nothing, not information, not influence, not cause and effect, can travel faster than the speed of light. At the time, most physicists didn't panic. They dismissed it. Einstein was 56 years old. Quantum mechanics was young, radical, probabilistic, and wildly successful. Many assumed Einstein was simply unable to accept it. The story hardened quickly. Einstein, the old genius, had lost his edge. He couldn't let go of determinism. He was resisting progress, but the paper didn't go away. 30 years later, a physicist stumbled across Einstein's argument and noticed something unsettling. It wasn't just philosophy. It wasn't just a complaint about interpretation. The prediction embedded in that thought experiment could actually be tested, not with metaphors, with real apparatus, real measurements, real data. When scientists finally ran the experiment, the result wasn't subtle, it wasn't ambiguous, it was shocking. Quantum physics really does involve influences that act faster than light. Not signals you can use to send messages, not violations you can exploit to break causality, but correlations that snap into place instantly, across any distance. Physicists found themselves forced to say something that had once sounded absurd, that nature itself seems to contain something like actions that go faster than light from one place to another. This story is about that realization, about how it came to be, about why it terrified Einstein, about why it confused Bohr, and about why, nearly a century later, we still don't fully know what it means. It is a story about one of the spookiest and most misunderstood experiments in all of physics, and it might even be the strongest evidence we have that reality itself does not unfold in a single world. To understand why this mattered so deeply to Einstein, you have to rewind even further. Imagine that the sun were to suddenly disappear. No explosion, no flash, just gone. How long would it take before Earth noticed and flew off into space? According to Isaac Newton's theory of gravity, the answer is immediate. Gravity, in Newton's view, acts instantaneously across any distance. If the sun vanishes, its gravitational pull vanishes at the same instant. Earth would instantly feel that absence and depart its orbit. Newton himself hated this implication. He called action at a distance an absurdity so great that no man with a competent faculty of thinking could accept it. But his equations worked, and for centuries, physics tolerated the discomfort. In 1905, Einstein realized the problem was worse than discomfort. It was fatal. Einstein discovered that observers moving at different speeds can disagree about when events happen. Two events that look simultaneous to you may not be simultaneous to someone speeding past. Both perspectives are valid, but if gravity acts instantly, this leads to paradoxes. Suppose you see the sun disappear and Earth fly away at the same moment, but another observer, moving relative to you, sees Earth fly away first while the sun is still there. To that observer, Earth departs orbit before the cause has occurred. Cause and effect reverse. Physics collapses. There was only one escape. Gravity cannot be instant. It took Einstein 10 years to solve this problem. In the process, he completely rewrote our understanding of gravity. Gravity is not a force that reaches across space. It is the curvature of space-time itself. Changes in gravity propagate as ripples, spreading outward at the speed of light. If the sun vanished, Earth wouldn't feel it for about 8 minutes. Another observer might disagree about the exact timing, but everyone would agree on the order. The sun disappears first. Earth responds later. Causality is preserved. This is why nothing can go faster than light. The speed limit isn't arbitrary. It is what keeps cause and effect consistent for all observers. By the time Einstein finished this work, all of classical physics obeyed this rule. Locality was saved. Then Einstein turned his attention to quantum mechanics, and everything broke again. In 1927, the architects of quantum theory gathered at the Solvay Conference. A photograph from that meeting is legendary. Nearly two-thirds of the people in that room would go on to win Nobel Prizes, and Einstein stood among them, unconvinced. Quantum mechanics worked astonishingly well. It predicted experimental outcomes with uncanny accuracy. But Einstein believed something fundamental had gone wrong. So he stepped forward with a thought experiment. Imagine firing a single electron through a narrow slit toward a circular detection screen. Quantum mechanics says the electron is described by a wave function, a mathematical object that spreads out through space. The wave isn't the electron itself, but it encodes the probabilities of where the electron might be found. When the electron hits the screen, you detect it at one single point. The probability of it appearing at any particular location depends on the amplitude of the wave function there. So far, everyone agreed. But then Einstein asked a simple question. Why doesn't the electron appear somewhere else a moment later? There is only one electron. We never see two detections. Quantum mechanics explains this by saying that when the electron is detected at one point, the wave function instantly collapses to zero everywhere else. The probability vanishes everywhere except where the electron was found. And that's the problem, because that collapse happens instantly, across the entire screen, no matter how far apart the points are. The measurement here must instantly affect the wave function over there. Action at a distance had returned. Einstein concluded that this mechanism was deeply troubling. He called it an entirely peculiar mechanism of action at a distance and said it contradicted the postulates of relativity. The room was stunned. Even Niels Bohr, the central figure of quantum theory, didn't immediately understand the objection. He later admitted confusion, but Bohr responded in his own way. Bohr believed physics was not about describing what nature is doing when we are not looking. It was about predicting measurement outcomes. The wave function, in his view, contained everything that could be meaningfully said. To ask what the electron really is when unobserved was, to Bohr, a meaningless question. Einstein despised this philosophy. He called it a tranquilizing religion. To him, the collapse of the wave function wasn't an answer. It was a confession of ignorance disguised as a rule. So in 1935, Einstein made one final attempt. Together with Boris Podolsky and Nathan Rosen, he published a paper that sharpened the argument to a knife edge. Today, it's known as the EPR paper. Imagine a single particle splitting into two, an electron and a positron. Their properties must balance. Their spins must cancel. But quantum mechanics says neither particle has a definite spin until measured. Instead, both exist in a superposition of all possibilities. Yet the two particles remain linked. Measure one, and the other's state is instantly determined, no matter how far apart they are. Einstein asked how this could be possible without faster-than-light influence. He proposed an alternative. Perhaps the particles carried hidden variables, pre-assigned instructions. The outcomes were already decided locally. Measurement merely revealed them. This would preserve locality. For decades, physicists argued. But there was a problem. Both interpretations made the same predictions. No experiment could distinguish them until John Bell. In the 1960s, Bell revisited the EPR argument and asked a different question. Could there be any experiment where local hidden variable theories and quantum mechanics disagree? The answer was yes. Bell showed that if you assume locality, then no hidden variable theory can reproduce the predictions of quantum mechanics. He derived an inequality. If the inequality is violated, locality must be false. When the experiments were finally done, nature chose quantum mechanics. The inequality was violated. There was no local explanation. The conclusion was unavoidable. Any theory that correctly describes the world must be non-local. Something in nature really does act faster than light. But here's the twist. Quantum mechanics avoids paradoxes by making outcomes fundamentally random. You can't control the result. You can't send a message. The correlations exist, but they can't be used to signal. Relativity survives in practice, but its spirit is wounded, and this leaves us with a choice. Either accept non-locality or abandon the idea that measurements have single outcomes. That's where many worlds enters. In the many worlds interpretation, the wave function never collapses. Every possible outcome happens. The universe branches. When you measure a particle, you become entangled with it. Different versions of you see different outcomes. There is no need for faster than light communication. The correlations exist because all outcomes already coexist. It sounds insane, but it restores locality. And suddenly, Einstein's deepest concern may have been pointing in the right direction all along. Bell himself believed non-locality was real, but he also believed we had misunderstood what that meant. Nearly a century after Einstein's thought experiment, we are still living with its consequences. Quantum mechanics works, relativity works, but together they pull reality in opposite directions. And somewhere in that tension, something profound is hiding. Because when the numbers don't add up, that's usually where the discovery is.